Um, I'm from Seattle. I work for the Cypress Seattle office. So today I'm going to talk about the 10 years of Cypress's journey in high performance computing. What we did wrong, and what we achieved now. Yeah, we founded in 1982, one of the early startups in Silicon Valley. Then we are primarily a memory company. But in 2000, we started shifting the focus to the programmable system on chips. We had a SunPower spin-off. Then we shipped 2 billion PSOC units in 2014. Last year, we acquired Spansion, or merger with Spansion. And this year, we bought the Broadcom IoT business. So that's the timeline. Yeah, I just introduced this slide just to tell you that what we are doing and where our products go. In fact, many of the products that we all use every day, one or two Cypress chips will be there. I can imagine all kinds of touch screen, captions controllers, USB controllers, starting from the flash drive USB controllers to the Tesla touchscreen. It's all run by the Cypress one or two controllers. This is Fitbit. All product lines in Fitbit use Cypress controllers. USB-C, we were the #1 and the first company who actually designed a USB-C controller. And we are the leaders in USB-C, and that is one of our biggest business now. So the products, I told you, we started with memory, then we had a SunPower investment, then many touch displays. With the Spansion acquisition, we got the automotive business, and with Broadcom acquisition, we have the Wi-Fi business. So that's where we are. We are like $2 billion at this stage. So the complexity of the project. So I know I said we are a memory company. We all know, right? Like how big is the growth in memory capacities? Like previously, like 120 MB flash drive was a big deal. Now you can have terabytes in flash drives. So that increase in capacity, memory capacity, actually created the complexity of the project also grow exponentially. So along with that, we have had the PSOC business, the programmable system on chip business, the USBs, captions, that all created the project complexity to a great extent. And it was a challenge for all the administrators and the architects to meet the expectation of the designers. I just introduced one other slide here, just to tell you that how complex and how important is our HPC environment is, because nowadays most of our chips, even if it is a memory chip, it goes into most of the automotive parts. We are in almost everywhere. Nowadays cars with sensors everywhere. So we have zero memory, zero margin of error, because you can't fail a sensor chip in an automotive field, right? So this goes through rigorous testing, simulations, and we have to do like 10 times testing than a normal chip that goes into any of the touchscreen or any of the other home appliances. So this is a huge business for us, and this is a huge challenge for us. So The design and verification runtime, in early 2000s, we had the complex memory chips. Then we had other piece of businesses started in 2000. So the runtime with the existing setup was going up to 36 hours. So these were like 1,200 simulations that we run every day. The designers usually design everything, run the code, write the tests, run the simulation in the evening. They wanted the results in the morning.
Take every other day off.
That's what they were doing. The productivity was so low. So
Nice work environment.
So yeah, 36 hours were killing us. And we know that for memory business, time to market is so key, right? So today's 32-bit is very small when you compare to like 2 months back. So that's we achieved. That's what we achieved from 2000 to 2016. I'm just comparing the similar complexity and similar structure, but right now this 7 hours is what we were doing 36 hours in 2005, 2004.
So now how much, but now you can do 3 times as much in a day?
Yeah, we do. But yeah, the complexity of the projects depends. This is an average of the different projects what we do, but
You don't just run 7 hours. So,
yeah.
So now you can do 3 times as much per day.
Right.
Okay.
And the 3 is actually an average number, or you can say that. But some cases.
Actually, it's more than that. I mean,
Yeah, it's more. Like 13x or 8x performance. I'll come to that. We have some slides on that. So the computing environment, what we have is like we have 11 data centers, 11 design centers. Each center got 1 data center, and 1,500 servers, or like 10,000 cores, and 4 petabyte of storage. That's what our current environment is. Okay. So now I'll start with the journey. In 2008 or before that, I should add like 2004, what we had. We were, is there anyone from the VLSI industry or semiconductor industry? 2004, we were running data from a Linux system with the RAID boxes. We were using one database management called Synchronicity, which is actually all links from all links for the workspaces for all engineers. So the one single database for everybody, and they check out into their local space and run it. But most of them are links. So that was the environment we had. But in 2008, we saw that the bottleneck. So we moved to NetApp. That was the most reliable at that point of time. But then we had this low performance. The cost was so high, and there's a capacity limitation as well. So we can't grow beyond that box capacity. So that was a challenge we had at that point of time, but was a reliable one. So this was our setup. We have the storage, LSF. We were using LSF since like long time back. So LSF and the end users, we all mounted to the NFS. That was the system what we had. Then, so since it's got some slow performance, we tried to do some other experiments. We evaluated different products. Finally found that Gluster at that point of time was a pretty good performance improvement. So we decided to go with Gluster. We did evaluation, testing, so it was all good. We implemented it, rolled out a couple of sites. Very cost effective because we used our own hardware. It's actually Dell boxes, it's a Dell Power or R610s. Then it was all going well, but when the data started filling up, like 1,000 simulations running every day, the there are like critical tools and simulations in the VLSI industry from Vendor Graphics and Cadence. So what happened was the cluster file system couldn't handle this kind of load, and then it created locks. And most of the time, when there's like 1,000 regressions running, half of the machine's compute farm goes stale. So this was a huge issue for us. One is a mount issue, and another one is the the corrupted file system. We can't even read from that. So this was a huge issue, and it's actually, you can imagine, right, when the storage goes out, then it's a big issue for us. So what we did, we moved some of the designers who was running regressions to NetApp back. Then some of them we could use their local workstation disks. So it was a huge issue for us. Then we deployed GPFs onto the same Dell hardware. So we bought the software and then installed onto the same Dell R610s. So this was a game changer for us. The performance was much better. It got native clients as well as the NFS client, because at that point of time, every engineers were using their own workstations. So to meet the cost, we moved all those workstation engineers to a native, NFS mount, and the LSF form was a native GPFS mount. Then, this was the performance numbers. So 8 to 13x performance for different type of projects. That was a significant change we saw immediately, because we had no time, because we got a corrupted file system, so we have to move. So we installed it like in 2 months, and that was a significant improvement for us. And since 2011, we actually ran on the same hardware we bought for the cluster till last year, or till this year. And then we got the ESS GL4 this year, and the performance is double. That is a significant, another improvement for us. So now designers are so happy that they get the regression results every day even before they leave from office. So they can launch the regression in the 2 o'clock and get it by 5 o'clock or 6 o'clock. So that was a kind of change.
Can they get 2 a day in now by doing that?
That may not work for us, because we need to put the simulation results to the design team, and then they have to fix it.
Okay, so there's a cycle somewhere.
Cycle, yeah, there's a cycle. So.
Okay.
So that's the improvement we had. These are the good numbers.
Still using NFS clients?
We actually changed the model a little bit. What we did is, for the end users, we just started giving laptops only. Previously, we had workstations, Linux workstations for every engineers. So now what they use is some critical users using Exit on Demand, and we have dedicated login servers, dedicated servers for the desktops in the compute farm. So that's in the server room, because the server room is actually a 10G environment for us, but the end user is a 1G environment. So we don't want a native client on a 1G network. So that's why we moved all this, the complete architecture. And now some of the designers who actually draw the chip with millions of transistors in it, so they have a latency issue. They don't want the mouse trail when they draw a line, because it's a very complex system, complex design. So only for them, we have the boxes, the Linux boxes, and most of the others, regular verification engine who write code, everything. So they all have the normal laptops, Windows or Mac laptops, and then they connect through real VNC or Exit on Demand to the LSF compute farm, where the GPFS is a native client.
Those login servers, they mount natively